Okay, morning, let's start. So again, just to recap, where are we and to where are we going? Or we used to say in Minas Gerais, cotô para covô. It's always a good idea to ask yourself, com coçô. Okay, yesterday we saw that the likelihood is a function for the support of data to a statistical model. So we have found a function that expresses the support that the data gives to a given model, a model fitted to this data. And then there's a method called the maximum likelihood method that fits statistical models by finding the values of the parameters that maximize the likelihood function. And we call these values of the parameters the maximum likelihood estimates. Today we will see true consequences of this to make some inferences about a model, a statistical model, once you fit it one by the maximum likelihood method. First, we will see how to compare the support data give to different models, and second, we will see how to make inferences about the estimated values of the parameters by this method, right? I would like to start recalling that any model is a simplified, a very, very simplified description of a much more complex situation. So you probably know the famous saying that all models are wrong, but some models can be useful. And there's another saying in a paper, in an ecology paper about neutral theory that says that models could be useful if they fail in an informative way. Okay? So that's the idea. We have a very, very complicated world outside. We are trying to figure out how to describe some aspects of this word with very simple descriptions. So the truth, or in the context of this course, the true process that is generated data is never known. Only when you simulate you can have some idea on the relationship between the truth and the models that we fit. So I will bring to you an example where the truth that I'm simulating, so in this case, I know the truth, is this model. So I have a normal variate that have its expected value as a function, which is not a linear function anymore. It's this function here of another variable x and a constant standard deviation or a constant variance, which is the same. So this, I'm depicting here the line of the expected value, which is this expression here, and the boundaries of the central 95% of this distribution, right? So I can, in a computer, I can simulate this process and simulate a sample of any size from this process that I will call the truth. Here you see a sample of size 21. And suppose that our brave modeler knows only or wants only to build linear models. And from the statistical point of view, from the point of view of statistical modeling, polynomial expression is also a linear statistical model. It's not linear in mathematical sense, but it's a linear model in the statistical sense, because all these models are just weighted sums of some other predictor variable. And so suppose that we have two models. This person decided to fit these two models to a sample taken from this unknown process. The first model is a polynomial of degree 2, and the other model is a polynomial of degree 5, right? Okay. So here are the fits of these two models. I'm showing only the lines of the expected values for these fits. And of course, you can see that the polynomial of highest degree have a very flexible function for the expected values. So you can make more flexible curves like that. And if you fit these models with the maximum likelihood method, and you can do that, of course, we know this already, you get the maximum likelihood of each of those fits, and the likelihood ratio between the model 1 and the model 2 is almost 40, which means that model 2 has 40 times more support from this data than model 1. What do you think about that? I would like to hear you. You probably are guessing my point here. We are talking about overfitting.
I was just going to say, we have more parameters, so we have more freedom to fine-tune our model.
Sure. Do you know another famous saying about fitting an elephant by a guy called von Neumann, which is actually one, he is a physicist, right? Von Neumann? Oh, Roberto told you. Okay, so do you remember?
Give me 5 points and I can draw you an elephant. Give me 6 and I can make its trunk move.
Yeah, that's it. So the more parameters you have in a model, the better is the fit, to the limit that if you have a statistical model or a mathematical model that has as many parameters as observations, you have a perfect fit. And this is a totally useless model, right? It describes perfectly the sample, but what's the point in doing that? We are not interested in describing the sample. We are interested in describing the process behind the sample, the process that generates this sample and can generate many, many other samples, right? So we have a problem here. Let me detail a little bit this problem. Suppose, and in this case, I can do that easily. We took many other samples and we fit the very same models to each of those samples, right? So what I'm showing here in light gray lines are 10 fittings to 10 different samples from this very same process. So you can see that for each of the samples, you got a very different line, right? What's happening here? It's the classic case of what we call overfitting of a statistical model. For Birren and Anderson, which is one of the texts we recommend for this lecture, overfitting is trying to make inference about unique features of your sample. Because, you know, each time you take a sample, you have some random variation by the sample itself, but not all of this variation is permanent, is a replicable feature of the process that generates this data. So for them to make inference about unique features of the data at hand, so your sample, as if they could be applied to the whole possible samples, is overfitting. So what's happening here is that this model is fitting also every tiny variation between samples, and this is not informative about the process behind that is generated this data, okay? And we do have some cues that this is happening if we take a look on the estimated values of the parameters by the maximum likelihood method, because you can estimate the values. So these are the commands to fit the model, and then you can ask to R or to any other statistical language a summary of this fit. A piece of the summary are the estimates of the parameters and also the standard errors of these estimates. Do you know what are these standard errors of the estimates. We are not talking about the standard errors of the data or the sample. Any guess? Or maybe you know, probably, what these standard errors are? Moise, certainly you know that, please. Oh, the mic. Great, Moise. You probably will explain this way better than I can do.
Here, the standard error is about the population, the true population. And when we are fitting the sample, we talked about the standard deviation. So the idea to resample the same sample many times is to expect that the standard deviation of this resampling distribution match the standard error. This is about the population. Então, standard error is like a standard deviation, but applied to all the population, not to sample.
Yeah, that's it. And this talks about the population of parameter estimates that you can get if you repeat the sampling and the fit many times, right? Is that right? Right. So if you remember, one of the properties of MLEs is the asymptotic normality, which means that if your sample is large enough, these estimates, the MLEs will have a normal distribution. What does it mean? That if you repeat the sample and the fit many times and record the estimates of the MLE values each time, if you plot the distribution of these values, you will see something like with more or less a bell-shaped curve, a normal distribution in the limit of large samples. So this standard error is exactly an estimate, it's an estimate of the standard deviation of this normal distribution that describes the distribution of the estimates, the MLEs, right? Is that clear? Great. So we can see here that these standard errors, especially for the parameters related to the highest powers in this polynomial expression, are pretty large. You can say here about a half or more than a half than the estimated value itself. If you remember, one of the properties of the normal is that you have 95% of the area of the normal between -2 and 2 standard deviations, right? Actually, it's 1.96, but okay, 2 for practical purposes. So you can say, for example, for this estimated parameter here, which is 100, that it has 95% of probability to lie between 100 minus 2 times 56, so it's negative. It could be negative, or plus 2 times 56, right? So it's a huge value for the standard error. This means that we have a lot of uncertainty about this estimate. So we can calculate this even if we do a single fit, because you can calculate this from the likelihood surface. It's the second, it has to do with the second derivative of the surface. And then you have a Q that you are estimating, okay, you are fitting, you are doing the best with each sample, but still you have a lot of uncertainty about these parameters. Why? They can vary a lot. You can see that. For each sample, these curves are very, very different. Why? Because the values of the parameters are varying a lot between samples. Why? Because this model is picking tiny differences, describing tiny differences between the samples that probably do not matter for us. Is that clear? It's kind of a little abstract. It's okay? Questions? Okay. So on the other side, you can have what Burhan-Anderson calls underfitting. Oh, please. Yes. Questions, questions.
It is a stupid question, but is that supposed to be a linear model?
Yeah, it is a statistical linear model. So the definition of a statistical linear model is different from the definition of a linear function. Okay, so recalling this is important because, well, it's kind of confusing. This is a statistical linear model because any model that you can write down, for example, like is a statistical linear model, right? So in this case, you have predictors xi that are xi to the power 2, xi to the power 3, and so on. But still, you can write this statistical model in this way. It's some constant times your predictor variable. So you can square this in your worksheet, for example, and call x2 equals, say, to z. Okay? It's the same for the statistical model. You are doing a weighted sum of these variables. Okay? Clear?
So just to... That is a statistical linear model, but it does not use a linear function.
Yeah, yeah. So
and
you can,
what is like giving me the curvy thing there?
What gives you?
Yeah, because usually
because you can see a cube. You can see cubes. Yeah.
Yeah.
The expected value is described by a non-linear mathematical function. It's a cube, right? But in statistical modeling, we call this structure a linear predictor. So we can say that this is still a linear statistical model. Paulina would like to say something.
The distinction is that it's a linear model because it's linear in the parameters. So the parameters are a linear combination of your predictable variables. So every time you have the sum of A1, A2, AI, but that sum makes the parameter you're trying to estimate, it's A. So it's linear in the parameters. It doesn't matter that you have like your predictor variable can be x squared, but the parameters are still linear. If you had like a1 times log of x, still linear. But if you had log of a, that makes it nonlinear. But it's linear in the parameters. That's key.
I'll also add that we can get curvy lines using other methods that don't involve like powers of predictors. We can have curvy lines using just correlations between the parameters in weird ways. So we can have really curvy lines and have a completely linear model on both parameters and predictors. Okay. So the shape of the resulting predicted value is not indicative of if you have a linear model or not.
But then, would that be an additive model?
Pardon me?
Is that an additive model? Additive?
Yeah, it is.
Okay.
It is an additive model. But you know, even if you have, good question, because even, well, this, for the purpose of statistical modeling, if you have a term like that in your model, adding to the other terms, this is a linear statistical model, if you have something like that, and even if you have let me stick to the notation. This is the product of two other predictor variables, and we call this an interaction term. But even if you have an interaction term or more than one, you still have a linear statistical model, linear predictor in our model. An example of a nonlinear predictor, say, because the parameter, one of the parameters is here. This does not have this form, right? And linear models, linear predictors are the best known structure for expected values in statistical models. So we always try to start with this kind of model. You can do nonlinear regressions as well, but it's usually a good idea to try some form of linear predictor first. Okay? That's why probably our brave ecologist was trying to fit polynomials to the data because polynomials are linear predictors. Okay, can we get back to the presentation, please? I think Thiago is switching. Well, I can do that by myself. It's no, here you are, but I think, yeah, okay. Done. So this is overfitting, and the likelihood ratio is still saying to us that this overfitting has much more support from the data than the other model, which is this, the expected value by the other model is this blue line. And we can have also underfitting, for example, if we try to fit a simple linear regression to this data, because, well, all the lines will be will look very the same, but in this case, I'm missing some very important feature of the process that generates the data. This feature probably shows up in any sample we take from this process. You can always say the cloud of points following something like that. We know that the truth is that. So this is a very important feature of the data generating process that probably shows up in any sample. And when you try linear regression, you are missing this feature. So this is underfitting. Your model has less parameters than you need to get a good idea of what is generating your data. So this is a good fit. This is not the expression for the true process, but still the fitted models captures the main features of this process, does not capture features that are of the sample. And if you take a look on the standard errors of the estimates, you will see that they are smaller compared to the value of the estimates in this case. So it's a Q that you have less uncertainty about these estimates that define each one of this fitting, each one of these Qs here. And makes sense because if you take a look at these curves, they do not see that they are varying in shape a lot. So for every sample you take, you will get, if you repeat the sample and fit it again and again, you will get more or less the same values for the estimates. That's why the standard error of these estimates are lower compared to the value of the estimate itself, okay? Okay, so we have what we call estimation bias in the likelihood ratios. And this guy tried to solve this problem, and he succeeded quite well. And it's Iritogu Akaike. And he deduced a correction for this bias towards overfitting when you use likelihood ratios to compare models with different number of parameters. And the correction is called the Akaike Information Criterion, AIC, and it's quite simple. It's just minus 2 times the log likelihood plus 2 times the number of parameters of your model, right? And this log likelihood is the value of the log likelihood evaluated at the value of the fitted parameters, which means this is the maximum log likelihood of the model. It's what you get when you apply the maximum likelihood method, right? So this is the value of the function that you maximize it or minimize it if it's minus log likelihood, 2 times plus the number of parameters. And what is really, really cool about AIC is that it estimates a statistical distance. What I want to mean with that, it estimates the distance. It's a way to say how different or how similar are two probability distributions. So it's a distance, and if the distance of your model to the true model is small, this is good. This is a good thing. And in this case, this distance is being measured, correcting for the bias that we have found for overfitting in the likelihood ratios, right? So AIC estimates a statistical distance. One of these between two distributions. One of these distributions is something that we don't know, which is the true distribution that generates the data. So there's kind of magic, or at least bootstrapping in the deduction of AIC, because we don't know the truth, but we can measure the distance of our model, which is also a probability distribution, right, to this theoretical truth. We can talk more about that if you want. And what's behind the scenes? IC is deduced. This is might be interesting, especially for physicists here. AIC is deduced from an entropy measure. So it's the Kullback-Leibler divergence, which is also called the relative entropy between two distributions, which basically means how much information that I have in the original process my model keeps. So how much information I lose when I try to describe this process with my model. So again, a little loss of information is good, so a small value of AIC indicates that your model is well supported by the data, right? Any questions about that? So we can use AIC besides the log likelihood ratio to compare models, to compare fits, because you will have the distance or the information loss of each model in respect to the same data. So as I said, the lower the AIC, the larger the support by the data for the model. And we have to decide to define which we will call a small distance from the truth. And there's what we call a canonic rule, so it's a kind of agreement. The same kind of agreement we make when we say that we will call significant any result of a significance test that gives you a probability less than 50% of being wrong if you reject the null hypothesis. So this is also agreement in different areas, in different fields. You have different values for the significance tests agreed. So in social science, it's common to use 0.1 for the significance threshold. Now in biology, and I think most of the natural science, we use 5%. Okay, so this is another of these rules. Most of the model selection community agreed that if you have a difference larger than 2 in the AIC of 2 models, you can say that one model is best than the other, is better supported than the other. If the AIC difference between 2 models is less than 2, you say that the 2 models are equally supported, equally well supported by the data. And 2 is this comparison when we fit many models, and then we can calculate the AIC of each one of these models. We calculate the delta AIC, which is only the difference of the AIC of each model to the minimum AIC in this set of models. So the best support or the more plausible model will always have a delta of 0. Okay? So if you have small samples, because the deduction of the AIC is also a deduction to the limit of large samples, but you do have a correction to use AIC for small samples, and what we call small samples is when the size of your sample divided by the number of parameters is less than 40. This is a rule of thumb to say, well, I have a small sample. So in this approach, if your sample is small or not depends on the number of parameters of your model, which makes sense, right? If you have few observations and try to fit a model which has many parameters than observations, this can lead to overfitting. So this correction takes care of this, and this term tends to 1 as your sample size increases, and in this case, you get back the original expression of the AIC, right? So another quantity that we can calculate from AIC values is the so-called evidence weights. So for each of the AIC values, you take the delta AIC and do this exponential and divide this value for the sum of all other values that you are, from the other models that you are comparing with AIC. So if you are dividing something by the sum of all other things calculated in the same way, that you will have a number that ranges from 0 to 1, and all of these numbers, these evidence weights, sum up to 1. So it's just a way to standardize the AIC values in a scale that is easier to interpret, because if one of the models, for example, has an evidence weight of 0.9, this means that all other models will share the remaining 0.1 evidence weights. So you can say that, wow, this model has a much larger weight of evidence than the other ones. So that's another way to look at AIC values, right? And another interesting thing is that if you think from a frequentist point of view, the weights estimate the proportion of times a given model will be the selected one, will be the model with the smallest AIC if you repeat the sample and the procedure many times. So if you have an evidence of 0.9, this means that if you repeat the procedure many times, so take another sample, fit the model again calculate all the models actually. The models again calculate the AIC of each of those models. 90% of the time, you will see that this model that have 0.9 evidence weight will be the model with the lowest AIC. You can easily simulate this and check this if you want. Okay, here's an example. Here's an example with the data we have fitted. And now we have 3 models here, and they differ only by their linear predictors. The green line, which is not easy to see here, but it's here. It's a linear regression. This is the second order polynomial, and this is the polynomial of order 5. So the commands to fit these models in R are here. Is just, well, it's, just writing down your models using the function LM for linear models that you already know. And then in this library that we will use to deal with the likelihood method, you have a function which is called AIC tab, to which you give all the objects where you store the results of the models. There's a bunch of options here, but basically this function returns this table here, so you can see the value of the AIC. You can see also the log likelihoods of these 3 models, and here you have the delta AIC, which is the difference between each AIC value and the smaller one, which is this one. And the table is ordered to put the model with the delta AC 0 in the first line. So we can see that model 1, which is the second order polynomial, is much better supported by this data if you take into account the bias, the overfitting bias, right? Questions? Comments?
I'll say that the AIC can also be thought at as of kind of an estimate of out-of-sample performance. So if you're interested in how your model will behave in data that you haven't seen yet, the AIC is a way to maximize that. So it's very useful when you're interested in prediction. One thing that's useful, we might, if we have time, I'll put something in the exercises, which is you can compare the AIC output with a cross-validation output. So cross-validation is when you separate your data in a fitting data set. So you fit your model to a part of the data set, and then you take the parameter estimates for that half.
It's not working.
Hello? Oh, we're back, okay. You take the parameter estimates from that half of the model, from the data, and then you check the performance on the other half, right? And this, for an overfit model, will perform very badly at that, right? Because it will have fit the particular aspects of half of the data, and it won't perform well in the other half. And the AIC is basically trying to approximate this. So cross-validation, AIC, these are all ways of trying to reduce overfitting, and a part of this is this generalization, right? You want to capture aspects of the data that are present not only in your particular sample, but in all other possible samples that you could have made.
I have a question. So yeah, I've never done AIC as a measure of out of sample. So basically you would use like this approach that Paulo is showing, and then you find that M1 has like then you find that M1 has a better support to your data, but so you would separate your data into in-fit and out-of-fit, and then you would use the AIC to select the best model, and then I don't understand how you would use it.
Okay, I guess I didn't explain cross-validation well enough. So what you do to select a model via cross-validation is you separate your data into a test data set and a trained data set. You use the trained data set to fit the model, and then you measure the performance of the predictive performance of the variables that you fit using the trained data set in the test data set, right? So you're using your coefficients to predict data that you've never seen before. And a model that behaves well in the test data set, the data that you've never seen before, presumably will generalize better than one that is overfit to one of those, right? So if you remember all of those different lines that Paulo showed, those, right? If you use one of those gray lines to predict the data that was used to fit the other, the performance would be awful, right? While the quadratic curve there would perform reasonably well in all of the subsets of the data, right? And so you would select the simpler model using cross-validation. Is that clear? And so, but this requires you to separate your data into two sets, and sometimes you don't have enough data to do that. And so the AIC is a solution that uses, it's all internal to the data, right? You don't have to separate anything. But it's theoretical, right? It's asymptotic, so it's not guaranteed to be optimal in small samples and things like that.
Yeah, that's cool.
But keep in mind this idea that the AIC is measuring predictive performance, right? You're trying to estimate the out-of-sample performance of your model. How well is it going to predict data that it has never seen before? That's one way to think about it.
Great, that's cool. Boys?
Just a comment. I would just like to say that with the test data, the test set, you have the data set, you will divide the data set in training set and test set. And you use the test set to cross-validate your model that you built with the training set. So with that test set, you can calculate the accuracy of the model and to select between three models, for example, you will show the model that has the best accuracy.
That's cool. We definitely will have an exercise on cross-validation in our tutorial. Sure. Wow. My comment is that cross-validation was proposed because it's usually easier to do than get back and get another sample, because the idea is just, okay, I fitted the model with this data, how good this model is to predict another data that I could sample from the same process. So usually you don't have time or money to get back to the field, for example, and get another sample. So you split your data, and there are many ways to do that. You split your data and fit the model for a part of the data, and then check if this model predicts, how this model performs in predicting the other part, right? So we will have a tutorial on this. It's a very nice way to think about AIC. Thanks, Diogo, and all of you. Okay. More questions at this point? Yes. Can you use the mic, please?
I don't know if you already said this, but the AIC, it's the differential that you showed?
It's the difference between two AIC values.
Between two? It's not between
but
the
it's
minimal?
the difference between each AIC values, which are here, and the minimum,
and the minimum
the
one.
smallest
the
AIC value that you have
The delta.
among the models you fit it to this data.
Okay,
right?
thanks.
So it's just a simple way to spot quickly which is the best supported model and how less well supported are the other models. So we apply our canonical rule here, and this model is definitely way best supported and provide much better predictions for other samples than this one, because the difference is larger than 2. And remember that these differences are in log scale. So to express this as likelihood ratio, you have to exponentiate this difference. So an exponent of 5, it's a big number, if you can calculate this. Rosa?
Well, I do not know if I lost this part, but why, when you have a delta AIC less than 2, why those models are equivalent? Why can we consider that delta AIC up to 2 is equivalent?
Well, it's because we have to agree some value, right? So you are saying, okay, AIC is a measurement of distance between 2 models, and this distance expresses how much information you lose with each model, but what is a distance large enough to say, okay, this model is better than that? We have to agree about that, because, you know, AIC ranges from 0 to infinity. So a distance of 1 is enough, a difference, a delta AIC of 1 is enough, of half. So the value of delta AIC2 is this kind of agreement, just like the agreement about significance levels in significance tests. It's something that you can change if you wish to, and you will have to justify. So for me, I would like to use a higher threshold, say a delta AIC of 2.5. Okay, you can do that.
Yes, I was thinking about the formula, and it has 2 times something.
Yeah.
So I was wondering if it has something to do with that.
Yeah, you can think like that, because, you know, if you add a parameter and this parameter does not increase your log likelihood function by 2 or more, this is probably overfitting. This is a way to look at this expression, right? But, well, I don't know if, well, the 2 threshold, the delta AC2 threshold was decided from one of those urn problems I showed you in the past lecture. So if you have a urn and if you have 2 hypotheses about the urn, all the balls are of the same color, or half of the balls are of one color and half the balls are of other color. If you take 3 draws and the three balls you pick from this urn are all of the same color, you have a delta AIC of 2. So the reason to disagreement is that many statisticians were asked to say how much balls of the same color would you need to definitely say that the hypothesis that the box has balls of only color is better supported. And most of the statisticians answered for this problem that they would go for 3 balls of the same color in 3 draws, and this is the delta AIC of 2 for this problem. So we use this threshold value for any other problem in general. So, but it's an agreement, as I said. There is no deduction to prove that this is better than using, say, for example, 2.1, 2.5, 1.9, or any other value. As far as I know, I don't know if some of you know some other strong theoretical reason to stick with the delta AC2 rule. Is there?
I'm saying this from memory, so I might be wrong, but I think the AIC of 2 in some nested models, like if you have a nested model, which means you have one model without a particular predictor and a model that is exactly the same, but with an additional term. So the first model is nested on the second. If you do that and you look at the likelihood ratio for those two, and for a likelihood ratio test with a significance value of 5%, it's about the same effect size as an AIC difference of 2. So it's roughly on the same, for this particular class of model, it's roughly on the same scale of the usual 5% rule. That's my memory of this. I don't know if you remember anything.
That's it.
Yeah,
Yeah, you're right.
So
But still, you are relying on another canonical agreement, which is the significance threshold. So
exactly. So it's as arbitrary as the other one, and even a bit more, probably.
Yeah, yeah. So if you like this significance value threshold, you would like to know that in some situations the delta AIC equal to 2 is the same, gets the same result. So that a nested model is something like that. Just to pinpoint an important concept. This is nested into that because this is a particular case of that where this parameter equals to 0, right? So you can use AIC to check if you have to include another predictor variable in a nested structure. So, and what you use to call the new model is something like that. You don't have the effect of none of the predictor variables. Okay. So this is a nested structure of linear statistical models. Where is my pointer? Here. More questions, comments? Right. So I have to. Thanks, Thiago. Sometimes I feel like a reality show here. Anyway, some important remarks on the use of AIC. You can have ties, so any model, any 2 models or more models that have delta AC less than 2 are considered equally well-supported models. So you can have ties, and this does happen a lot in model selection, at least in my field in ecology, because samples are not large enough to distinguish between 2 models when they differ by, say, just 1 parameter. So usually these ties are telling us that the data does not have enough evidence to distinguish which one of these models, tied models, are best supported. Model selection is not a statistical test. It's not a significance statistical test. Meanwhile, the results of model selection in some cases match the results of some significance test, but it's not. You don't have a significance value, you don't have a p-value, and when AIC and model selection with AIC was still not much used in my field, it was a very common request from referees, where's your p-value? You don't have a p-value, so on, so we have to explain that for the editor or for the referees. So model selection is restricted to the competing models, so it's a kind of competition. So all you can say is that among the models you choose to describe your data, which one is the better supported. But if you have only bad models, all you will have at the end of the model selection with AIC is the least bad of these models. AIC does not express an absolute measurement of goodness of fit, exactly because by the same reason, you can have a model that fits the data much better than the models you are considering, but if this better model is not included in your models, pardon me, model selection, you will see only, you will never know that this model is better. So you cannot use, this is very, very, very important. AIC uses like the likelihood function, right? And the likelihood function is conditioned to the data set. So there's no point in using AIC to compare models fitted to different data sets. You can only think about model selection in the way, how to express? Well, I have the same data, I fitted different models to this very same data, and I want to know which model is better supported by this data. If I change the data set, you have another model selection. And you cannot compare models fitted to different data sets, and this implies too that you cannot use AIC to compare a model, say, fitted to the data and to the logarithm of the data, because these are different data sets, right? So this is very, very important. It's a common mistake to compare, for example, a model fitted to, yes, the values, the observations, and the logarithm of the observations. This does not make sense. Questions?
But if we were, for example, going back to the same ecological site, the next year.
I think we can retire this one. Okay.
For example, if we went to the same ecological site where we took our data the following year, can we use AIC to compare those, for example, two different models created with the same, which one would imagine is the same source of creation of data?
Yes, only if you lump the two samples in a single data set. So from the point of view of using AIC in a frequentist approach, right? So from a Bayesian approach, it's totally different. You can see the second sample. Well, the first sample gives you some prior model, and you can get your second sample and ask how this second sample changes your prior knowledge. But this is Bayesian that Diogo will show you in the 2 days forward. But for the AIC, you can lump the two samples, but you cannot fit a model to sample 1 and then fit the model with the sample 2 and use the AIC of the two models and say which one is better supported. So the idea behind that is that all that you can do with data about the statistical models is to say how well supported is a model by a given data set. So it can happen, and it does happen, that when you get back and get another sample, a different model is selected. So in this approach, you don't have no statistical work to do that. You can discuss this, right? Okay, my samples support different models, but you do not have any statistical procedure to do that in this approach. You do have in Bayesian approach. Is that clear? Yes. Wonderful. More questions, comments? Yes.
The AICs, I mean, I've done it before, but it's a good measure of a criterion of model selection, even if the models are not nested within each other.
Yeah, for AIC, for some tests, like there's a test called the likelihood ratio test that works only for nested models. But for the AIC, you are free to compare any model. You can, any model that differ in the predictors like that, or a model that uses a Poisson distribution to a model that uses a log normal distribution, for example, and so on. Totally.
So the only limitation is that all the data have to come from the same data set.
Yeah,
okay.
yeah. That's it. Okay, oh, please.
So, my doubt is if we can test a model with different distributions like normal or Poisson, and we can use the AIC to determine which distribution is better for our data.
Yeah, you can.
You can do that?
Definitely, yeah. All you need to do that is more than one statistical model fitted to the same data. And we know that statistical models are just mathematical objects that assigns probabilities to observations. So a normal does that, a Poisson does that, so you can compare models that differ in the underlying distribution assumed to describe the variation of the data. So Paulinha will show how we can extend the linear model to some other distributions, which are the generalized linear models, for example. So you can, definitely. And I think this is one of the main strengths of model selection with AIC. More questions, comments? Okay. So let's talk a little bit about, well, with this I finish my considerations about inference, about different models. And let's imagine now that we spotted the model that is better supported by your data, and now you can make inference about the parameters of these models, right? And the basic tool to make inference about the parameters of the models is what we call log likelihood profiles. So in the y-axis, we plot, we put the negative relative log likelihood, which means that I take the logarithm of the likelihood function minus this, and then I standardize this measure to have the value of 0 at its minimum. Is that clear? So profiles is not exactly a slice, a straight slice of the likelihood surface, but you can think like a profile. Yeah, it's a slice, but not exactly a straight slice of a very complicated surface, because the surface has as many dimensions as parameters in the model. So it's pointless to try to take a look on the whole surface, and we try to slice it and look the behavior of each one of the parameters, look the behavior of the likelihood function in the neighborhood of the minimum of this function for each one of these parameters. So what we'll get is this. We will see in our tutorial how to plot a likelihood function of a fitted model for all the parameters of these models. And what this profile show us is that, well, you have a minimum value for the profiled log likelihood. At this minimum value, you have the value of the parameter that minimizes this function is the value of the maximum likelihood estimated. So in these models, the MLE of this parameter sigma is about 0.62, more or less, right? But if I fit a model with a value of this parameter set to 0.7, this is not much less supported by the data than the maximum likelihood estimator, right? The same for, for 0.6 and so on. So what we can do here is to put a straight line, a limit again, at the threshold of 2, and again, it's the same threshold, actually. And so it's an agreement. And all the values within these 2 units of negative likelihood, so all the values within below this line, this horizontal line here, can be considered equally plausible, equally well supported by the data. So you have a plausibility interval. You can say that it's plausible according to this data that sigma has a value between a little more than 0.5 and 0.8, right? So it's a kind of interval, similar to the confidence interval, but it's not. The definition is totally different. Here you have an interval, you have a set of values that provides you an equal plausible estimation for this parameter. Yes?
So you make this plot for the negative log likelihood, but for a single parameter. And so you have to set all others to some constants.
Not exactly. It's, let's see. If we have time enough, I can explain this a little in a more detail, but it's not exactly. It's an approximation of, you can see this as you described it, but if we do like you described, we are taking a straight slice of the surface, right?
Yes.
It's not exactly that. But still, it's more conservative than that because the intervals will be wider doing profiles, likelihood profiles, than doing likelihood slices. But we can go get to this later.
And just another question. Where does this 2 come from? Why 2 units of?
It's the same threshold we have already discussed. It's the very same threshold. It's in exponential, in log scale, in the exponential scale. A difference of 2 between 2 log likelihoods is the same threshold that we use in AIC to compare models, right?
Okay.
So it's canonical again. If you like higher threshold, say for example 3, which means that you are looking for a likelihood of up to exponential of 3, which is, can someone calculate this? Exponential of 3? It's more or less, you can do that, so it's just a matter of cutting this profile here, and you will, of course, have a wider interval. So if you want to be more conservative, you can do that.
Okay.
Right? Okay, the first thing we have to look at in this kind of profiles is if they behave like that, so they have a very defined minimum. They look like more or less a good parabola, so this is a good fit. But if you have things like that, this is telling you that you have some problem with fitting. Usually, you have a model with too many parameters for your sample size. So the computer and the optimization routine is getting trouble to fit your model. And you have profiles like that have a lot of uncertainty in the lower bound of the estimate, for example. Among other things like local minima, like here you have a minimum, here you have other minimum. All of this is telling you that you have a very tricky likelihood surface. So it's an alert. The better you can do here is to use models with fewer parameters or get to increase your sample size. So this is the message. But if you have a likelihood looking like that, it's it's okay. You can go ahead and think about the likelihood interval or the plausibility interval. So to finish, just an example of how to use this to make some inference about a model fitted to the data. I took this from this paper, which has a very simple hypothesis that the total biomass of ectoparasites, so fleas and this kind of bugs that are ectoparasites of birds, if you pick all of these parasites from the bird probably will thank you first. And then you can calculate the mass of this bunch of ectoparasites. And there's a very simple hypothesis that the total biomass of these parasites will be proportional to power of 2/3 of the surface of the bird, you mean. The surface, the skin surface of the bird determines the maximum amount of parasites that can, parasite this bird. Okay, so it's a very, very simple hypothesis that they tested with this data, which was the average body biomass of 42, it's a good number to make a study, right? So it's the average body biomass of 42 bird species and the average mass of ectoparasites picked up of each of some individuals of all those 42 bird species. And so you can test this hypothesis by doing a linear regression at log scale. Because if you take the log of the average parasite biomass as a function of the log of the average body mass, the slope of this linear regression will be the power of the proportion between these two quantities in the original scale, right? So it's simple as that. It's just a matter to fit a linear regression here and see if the slope is close to this value here. Okay, so that's inference, and here's the linear regression fitted to these points, and here is the log likelihood profile of the slope of this regression. What would you say about that? What would you infer about this data or the process that is generate this data with this likelihood profile? This is the expected value for the slope of this regression. Pardon me? Oh, está fora, sim. So this data does not support this hypothesis. We can infer that, right? So it's not plausible if we use this threshold. It's not plausible that the biomass of ectoparasites scale to a power of 2/3 to the mass of the host bird. Okay, this is an example of a very, very simple inference that you can do. Log likelihood profiles provides you these intervals to make these inferences. And if there's a function in R to calculate the profiles, and then you can, a question?
But maybe if you continue explaining, my question will go away. So I'll ask again in a minute.
Let me guess, you're going to ask about confidence intervals?
No.
No? Oh, so this time, okay. So let me talk about confidence intervals. Yes?
Well, in the previous, because I don't think my question is about confidence intervals. How can you argue based on these things if the data is not supporting your hypothesis or your model is wrong? What's the difference between arguing these two things, you know?
Yes.
Do you understand my...
Yes.
my
That's a great question. Well, I would like to hear more people in this room, but from my point of view, you have to think carefully about the models you want to fit to the data, and these models should have some theoretical reason to be proposed. So I saying that because, you know, well, let's take a look on the data. Okay, looks like there's a relationship, so let's try a linear regression. This is not a strong reason to fit a linear regression. I picked this example because you have some theory that says you have a scale law that in log scale boils down to a linear regression. So in this case, you have a truly theoretical reason to fit a linear regression. But if you try if you try many models with no specific reason, you eventually will find a good fit. But what does it mean? How can you interpret the parameter interval of this model? So I think the story begins with carefully defined models.
Can I extend my question a little bit? So in this case, you're saying that there is a background to argue that this should be linear, but my mind goes wild with this one because you don't even know if this linear coefficient is supposed to be positive or negative. So you don't know if the relation is positive related or negatively related. So, and by the profile that we're looking, both are plausible, but they're not. You see, there are like many problems that I'm seeing.
Sure, absolutely. Well, first, what does it mean? It means that if the process that generates the data is something like that, it's a linear, the expected value is a linear function of log average body mass of the birds. If this approximates the true process that we don't know that generate the data, this data or this sample does not support my hypothesis on the power law in this case. But you spotted another thing that nobody has spotted so far, that it's plausible that this slope is negative. It is, according to this data, it is. So, well, what would you conclude with that?
That your hypothesis is wrong.
Yeah, could be that you don't have any relationship between these two quantities, right? It's plausible according to your model, because you know your model allows to a zero slope. So your model includes the possibility that there is no relationship between body mass, ectoparasites mass and body mass, right? And your data says that this is plausible. According to this data, this is plausible. So
I understand.
I
it
agree
depends
with
on
you.
a lot of things, the arguments.
It's a nice inference that you can do with this result, yeah? I totally agree.
Yeah, so I don't think I understood really well this graph on the left. Like how to relate these two graphs to tell that my data doesn't support the model.
Okay, can you help me a little bit and say what you get from this plot so we can start from this point?
Maybe not
almost
much.
Nothing?
Yeah, probably.
Okay.
No, let me guess some things. Like understood her question, and I understood everything you said about it being plausible that it is a negative or a positive slope. But then there's this little arrow in this graph from the left, which represents where the slope is.
Where the slope should be if the hypothesis of the so this is not part of the likelihood plot. I just added this to pinpoint the theoretical, the expected value of the slope according to the hypothesis that motivated this study.
Which is
so
this?
it's
Which is this?
2/3 here. Which is that? Sorry, this is that.
Oh, okay. Okay.
So it's just to show that this falls outside the likelihood interval or the plausibility interval. So if this falls outside, so it's not a plausible value for this slope according to this data. That's what we can infer. One of the things we can infer with this likelihood profile. The other thing is that it's plausible that there is no relationship, or even it's plausible that this relationship is a slight negative instead of being positive, which is weird, right? The larger the bird, the less ectoparasites it has. I don't know. Well, might be some interesting biological reason for that. I don't know. Better?
Well, I was thinking about the y-axis, because I remember the graph of the likelihood function.
Mm-hmm.
We have a concave down.
Yeah.
And we put negative, so it is concave up now.
Yeah, that's it.
But what is the relative, what is the standardization you make to...
Relative.
Is so.
Yeah, because the minimum value here is set at this scale, is a scale that just sets the minimum value of the negative log likelihood to 0 at its minimum. Because, you know, if you calculate the likelihood, it will give you some number. But all that matters is that the minimum value of this function here, and what's the values of the other values, the other values of the likelihood function close to this minimum. So you standardize making the minimum equal to 0. So this is why this is called relative to the minimum. Relative to the minimum, this is the difference between the minimum and this point is 2. I don't know what's the raw value of the likelihood, but I know that the difference between these 2 points are 2 unities of log likelihood. And that is all I need to make this kind of inference. That's it.
We can have these profiles that do not cross 0. In this case, it crosses 0 because our hypothesis, our data has a slope that can be 0.
Yeah, if you take a look on the cloud of points, sounds reasonable that you can have a slightly negative slope or even a 0 slope for this data. Looks like that's because the data is so spread that likelihood is telling us it's plausible. Could be. If you give me this model, I can say that it's plausible that this model might have a 0 or even a negative slope. More questions? Yes.
Yeah, I wanted to know if we could use the negative relative log likelihood plot to formulate a new hypothesis of if we could use that plot to formulate a new hypothesis on the real slope. Like, okay, 2/3 is a bad hypothesis. Can we use that one?
Well, I don't know. Again, the views in this room probably are different, but my view is that in general, it's not a good idea to make a theoretical hypothesis based only on data, on patterns that you see in your data, but you do not understand. If you cannot provide a general explanation for that, if you can, okay, it's reasonable that the larger the bird, the less fleas this bird has because this and this biological process. Now, I can figure out some general explanation based on the biology of the system. Okay, so you can think about that. You start thinking about that after looking at that, but now you have a general hypothesis that has some background. It's baked, well, it's baking from biological knowledge, not only about, okay, now I see that the slope can be 0 or even can be negative, so my next hypothesis is that it can be 0. So it's kind of circular reasoning if you refine your hypothesis only based on your data, right? So you have to, okay, data can change the way you view a system, but after data does this to you through your previous knowledge about the system, you have to reformulate your model, your theoretical model, and then go to get more samples and check if this model is better than the previous one. Again, we are venturing in the Bayesian way to look at these problems, which is a very nice way to solve this kind of problem. So the data is telling me something something unexpected, what I do with that, right? Great questions. Maybe well, I expressed my views on using statistical models. I'm aware that there are other views about that. So, for example, I think the whole field of data science is basically about formulating hypotheses driven by the patterns you find in data, and people, well, are more concerned on a good prediction than to explain what this pattern is in this way, right? I don't know if is there machine learning as well goes to this direction, right? Okay, that's it. So we don't have more time, but just to remark, and maybe we can include this in our tutorial, that if the likelihood profile looks like a well-behaved parabola, the limits of the plausibility interval of the likelihood interval will match the limits of the traditional confidence interval. So the definition of these two intervals are quite different. They are different things, but they do match if you have a sample large enough. So it's okay if you think your sample is large enough to look at confidence intervals and think that plausible values are within this interval, okay? We can talk more about this later. So the reading for this lecture, I strongly recommend this book, which is Buchanan and Anderson book about model selection. The first 2 chapters are a wonderful explanation on AIC and model fitting, and a very nice way to use models, statistical models, to test hypotheses and theories in any field of science. Okay? Thank you for your attention.